Hello, we will discuss now the method of sections. Normally for a long span, there are times that we need to determine one or two or few of the members. Uh, that we would like to determine the forces involved. So the method of sections would be the short way of looking for it. As a background, if the forces in only a few members of the trust are to be found, the method of sections generally provides the most direct means of obtaining these forces. This method consists of passing an imaginary section through the truss, thus cutting it into two parts. Provided the entire truss is in equilibrium, each of the two parts must also be in equilibrium. And as a result, the three equations of equilibrium may be applied to either one of these two parts to determine the member forces at the cut section. When the method of sections is used to determine the force in a particular member, a decision must be made as to how to cut or section the truss, since only three independent equilibrium equations can be applied to the isolated portion of the truss. Try to select a section that, in general, passes through not more than three members in which the forces are unknown. Again, try to cut a section that will not be more than three members in which the forces are unknown, because we only have three equations of equilibrium. As an example, if the force in member GC of the truss below is to be determined, the section AE will be appropriate. So we cut the section from the top, from BC to GC to GF. The pre-body diagrams of the two parts are shown on the right. In particular, one that note that the line of action of each force in a section member is specified from the geometry of the truss. So you can just follow the geometry of the truss even if you have to cut it, since the force in a member passes along the axis of the member. Also, the member forces acting on one part of the truss are equal but opposite to those acting on the other part. This is the third law of Newton. As shown, members assumed to be in tension, that is FBC and FGC, are subjected to pull, whereas the member in compression, that is GF, is subjected to a push, that is at the bottom, because this is a bracket truss. So we expect that the top chords will be in tension and the bottom chords will be in compression, since we have a vertical force applied at the end of the bracket. For the correct sense of a non-member force, as in the method of joints, there are two ways in which one can determine the correct sense of a non-member force. The first method is that always assume that the unknown member forces at the cut section are in tension, that is pulling on the member. By doing this, the numerical solution of the equilibrium equations will yield positive scalars for members in tension and negative scalars for members in compression. The second method is that the correct sense of the unknown member force can in many cases be determined by inspection. Again, I want to emphasize this one. You need to develop that skill by inspection, so that you will be able to determine directly what particular force a member of the truss is carrying. For example, FBC is a tensile force as represented in figure B above, this one, FBC. Because if we cut that section BC, what will happen to the truss is that the truss will rotate counterclockwise. So the joint B tries to go away with C, so it should be in tension. The procedure for analysis, we need to draw again the pre-body diagram. For the pre-body diagram, you make a decision as how to cut or section the truss through the members where forces are to be determined. Step 2. Before isolating the appropriate section, it may first be necessary to determine the thrust external reactions so that the three equilibrium equations are used only to solve for member forces at the cut section. Then drew the free-body diagram of that part of the section truss which has the less number of forces on it. Use one of the two methods described above for establishing the sense of an unknown force. For the equations of equilibrium, there are two steps. First step, moments should be sum about the point that lies at the intersection of the lines of action of two unknown forces. In this way, the third unknown force is determined directly from the equation. Step 2, if two of the unknown forces are parallel, forces may be summed perpendicular to the direction of these unknowns to determine directly the third unknown force. So for an example, we would like to consider again the thrust in example 5.2 of Seaward, and suppose only the forces in members AC, BC, and BD are required. Of course, for this particular thrust, we are quite familiar already, but I just want to uh, reiterate, if we have to cut at member AC, try to develop your skill. Okay, so if we have to cut member AC, what will happen to the thrust? It will rotate clockwise. Since it will rotate clockwise, then C is moving away from A. So member AC should be in tension. If we cut member BD, then again the the thrust will tend to rotate clockwise. So the joint D will move towards B. So this member BD should be in compression. So with by cutting BC, uh, if you cut BC, then the shape ECDB will try to have a parallelogram shape, meaning point C is moving towards point B. So this is in compression. So by working on that way, we can always find the possible direction of the force and if it is tension or compression. Here is our solution. If we have to cut that portion, we try to use again a human figure at the top to hold the truss. So this is in tension, and so with the human at the bottom, which uses compression. A cut is made through the structure which must pass through the member whose force is required. In this case, all the required members can be cut at one go. However, sometimes several cuts may be required. So it's not necessarily that it's only one cut. You can also cut several, as long as there are only three unknowns, because we only have three available equations. The forces on the structure to the left of the cut are completely ignored. In this case, we only consider the right side of the structure, but of course if you want you can do it on the other side, but for this particular problem, uh, it's only uh, it's only possible if we have to consider the right side of the graph or of the truss. The forces in the three cut members must be sufficient to put the remaining sections of the structure into equilibrium. So here is the diagram of the truss showing the different forces and including the slope of member CB. The three basic equations can now be used to solve the three unknown forces. By applying this intelligently, it is possible to avoid having to solve simultaneous equation. Again, we always encourage solving a simultaneous equation because it's really a source of error. But I'm not saying it's wrong. Okay, if you want, you can do it. If you really like solving simultaneous equation, then it's not really a problem. But we try to minimize our errors. So that is why we always encourage you to solve problems in with one unknown only. So to find the force FCE, that is the tension at the top, it is obviously advantageous to eliminate the other two unknown forces, FCB and FDB. And how do we do that one? Because these two forces intersects at point B, so we can take moment at point B. So summing up moment at point B, so there will be three forces involved. The external force 10 will create clockwise direction, so that's 10 times 1.2, and the other 10 times 2.7, which is equal to the counterclockwise effect of FCE, FCE times 1. So in this equation, we only have one unknown, that's FCE, which is equal to 39 kilonewton, which is tension. Again, the result is positive, so it's tension. Otherwise, if you were able to commit an error by inspection and you are saying it's tension, but the result is negative, then you can just change it from tension to compression. Likewise, to find FDB, the lower chord take moments about point C, because FCE and FCB will pass through joint C. So here, if we take moment at point C, there will be only two forces. That's 10 times 1.5 will create clockwise moment, and the other one, FDB times 1, which will also cause counterclockwise bending. So in this case, FDP is equal to 15 kilonewton, which is compression. To find FCB, the last member force, the above strategy cannot operate as FCE and FDB are parallel. So you cannot just take moment here because they are parallel. So a simple alternative is using a vertical equilibrium to eliminate FCE and FDB. Again, we are doing this because there might be some errors when we solve FDB or FCE. In that way, our equation should be independent with the two unknowns. So here, if we sum up vertical forces, we have three forces only. The the component of FCB, which is vertical, using the slope 1 over square root of 2.44, which is equal to 10 plus 10, that's 20. So here, FCB is 31.24 kilonewton, which is compression. Okay, so we were able to successfully compute the three forces with independent equations. Again, we are not really sure with our results, so if you want, you can use other equations available to check your work. Okay, here is the basic strategy we adopt. To eliminate the effect of two parallel members, some forces perpendicular to them. To eliminate the effect of two members whose lines of action intersect, take moments about the intersection point. Okay, so that's all about the methods or solving a 2D truss. Anyway, in the next lecture, I will discuss also how to use graphic statics to solve 2D truss, and also I will discuss the using software. But by this time, we will discuss the space truss. Space truss is consists of members joined together at their ends to form a stable three-dimensional structure. Actually, it has similarity with the 2D truss, because in a 2D truss, it's a triangle with three members and three joints. And in order it to be simple truss, we just add every two members with one joint. So in similar manner with the triangle arrangement in two-dimensional truss, the simplest element of a stable space truss is what we call tetrahedron, this one, with 1, 2, 3, 4, 5, 6 connecting members together with 1, 2, 3, 4 joints. Any additional members added to this basic element would be redundant in supporting the force P. A simple space truss can be built from this basic tetrahedral element by adding three additional members and another joint, forming multi-connected tetrahedron. So unlike with the 2D, two members, one joint here, three members, one joint. For the determinacy and stability of 3D truss, realize that in three dimensions there are three equations of equilibrium available for each joint. Then for a space truss with J number of joints, that is, you have to multiply the number of joints by 3. So we have 3J equations which are available. So this is the only difference with the 2D, because in 2D we have two equations available for its joint. So that's 2G. Here we have 3G. So if the truss has B number of bars and R number of reactions, then like the case of planar truss, we can write B plus R is equal to 3G. If it is equal, then statically determine it, but you check the stability. If B plus R is less than 3G, then the truss is unstable. But B plus R is greater than 3G, it is statically indeterminate, but plus you have to check the stability. For the external and internal stability of a 3D truss or space truss, the external stability of the space truss requires that the support reactions keep the truss in force and moment equilibrium along and about any and all axes. This can sometimes be checked by inspection. Although if the truss is unstable, the solution of the equilibrium equations will give inconsistent results. So this is your red flag. For the internal stability, this can be checked by careful inspection of the member arrangement, provided its joint is held fixed by its supports or connecting members so that it cannot move with respect to the other joints. The truss can be classified as internally stable. Also, if we do a force analysis of the truss and obtain inconsistent results, then the truss configuration will be unstable or have a critical form. Here are the assumptions for design. The members of a space truss may be treated as axial force members, provided the external loading is applied at the joints, and the joints consist of ball and socket connections. This assumption is justified provided the joint members at the connection intersect at the common point and the weight of the members can be neglected. In cases where the weight of a member is to be included in the analysis, it is generally satisfactory to apply it as a vertical force, half of its magnitude applied to its end of the member. So for the force analysis, the supports of a space truss are generally modeled as a short length, plain roller joint, slatted roller joint, or the most common ball and socket joint. Each of the supports and the reactive force components are shown in the next table. So for the short length, there's only one force reaction here. For a roller, again, there is also one which is perpendicular to the surface. And for a slatted roller constraint, there are two forces that is perpendicular to it and along the surface. For the ball and socket, there will be three components along the X, Y, and the Z axis. For the analysis of this, it's also important that we need to determine the components of the force. Since the analysis of a truss or space truss is three-dimensional, it will often be necessary to resolve the force in a member into components that are acting along the X, Y, and Z axis. For example, in the figure, member AB has a length L and known projections X, Y, Z along the coordinate axis. These projections can be related to the member's length by the equation, just like the Pythagorean theorem, that's L is equal to the square root of X squared, Y squared, and Z squared. So that the force F, which acts along the axis of the member, can have a components determined by proportion as follows. So the component along the x-axis is simply equal to x over L. X over L. Fy we have y over L and Fz z over L. Notice that this requires the resultant force F to be equal to the square root of Fx squared plus Fy squared plus F2 Fz squared. By the way, sorry for that. I was able to forget to multiply these components by f. You need to multiply these components by f. It's not only about the proportion x over l. It's important to multiply it with f. Also, for the zero force members, it's important that you will recognize this one. There are two cases. Case one, if all but one of the members connected to a joint lie in the same plane. Take note, all members connected to a joint lie in the same plane and provided no external load acting on the joint, then the member not lying in the plane of the other members must be subjected to zero force. Remember that one, if all the members connected to a joint lie in the same plane and has no external load, then the other member not on the plane is subjected to zero force. So the proof of this statement is shown in the figure below, where members ABC, this one ABC, lie in the XY plane, this one. Since the Z component of FD must be 0 to satisfy summation forces Z is equal to 0, member D must be a zero force. By the same reasoning, member D will carry a load that can be determined from summation of forces Z is equal to 0 if an external force acts on the joint and has a component acting along the Z-axis. The other case is that if it has been determined that all but two of several members connected at a joint support zero force, then the two remaining members must also support zero force, provided they do not lie along the same line. This situation is illustrated in the second figure, where it is known that A and C are zero forces or zero force members. Since FD is collinear with the y-axis, then application of summation forces x is equal to 0, and summation forces z is equal to 0 requires the x or z component of FB to be 0. Consequently, FB is equal to 0. This being the case, so FD is equal to 0 since summation forces y is equal to 0. We have this procedure for analysis for a 3D truss. We have the method of sections and the method of joints. For the method of sections, if only a few member forces are to be determined, this method is used. When an imaginary section is passed through a truss and the truss is separated into two parts, the first system acting on either of the parts must satisfy the six scalar equilibrium equations. By proper choice of the section and access for summing forces and moments, many of the unknown member forces in a space truss can be computed directly using a single equilibrium equation. In this regard, recall that the moment of a force about an axis is zero, provided the force is parallel to the axis or its line of action passes through a point on the axis. For the method of joints, generally, if the forces in all the members of the truss must be determined, the method of joints is most suitable for the analysis. When using the method of joints, it is necessary to solve the three scalar equilibrium equations at its joint. And since it is relatively easy to draw the free body diagrams and apply the equations of equilibrium, the method of joints is very consistent in its application. As an example, we have this space truss, and we would like to determine the force in each member of the space truss. The truss is supported by a ball and socket joint at A, here, and a slotted roller joint at B, and a cable at C. So you can draw the free body diagram with the corresponding support reactions. At the ball and socket, we have 3. At the slotted roller joint at B, we have 2. And a cable at C is 1. And with the external force 600 pounds applied at joint E. So here we have the example. The truss is statically determined by computing B plus R is equal to 3G, because 9 plus 6 is 15 is equal to 3 times 5, which is also 15. For the support reactions, we can obtain the support reactions directly from the free body diagram of the entire truss using the equations of equilibrium. So you can sum up moment along y-axis, here along the y-axis, and it will result to 600 times 4 plus bx times 8, where bx is 300 pounds. Also, you can sum up moment along the z-axis, around the z-axis. So we have 600, cy, nothing. So cy is equal to 0. And if we sum up moment along the x-axis, then the forces involved will be by and 600. So by times 8 minus 600 times 8, where By is 600 pounds. If you sum up forces along the x-axis, we have two forces, Ex and Bx, where Bx is computed about 300, so Ax is also 300. If you sum up forces along the y, we have Ay, By, and Cy. And Cy is equal to 0, so we only have Ay and By. And By is 600, so By is 600 pounds also. And lastly, summing forces along the z-axis, we have Ez and 600. So Ez is equal to 600 pounds. For joint B, because we have joint A, joint B, joint C, joint D, joint E, we can look at joint B first. We can begin the method of joints at B since there are three unknown member forces at this joint. The components of FB can be determined by proportion of the length of member BE, as of course indicated in equations 3 to 5. So if we have to apply the summation of forces from x, y, and z, we can get these equations and the corresponding values of the forces. Also at joint E, using the result for FB, which is 600 pounds, which is in compression, the pre-body diagram of joint E is shown here. And we can apply summation forces Z, Y, and X to determine the corresponding unknown forces. And the joint D, by inspection, the members at joint D support zero force since the arrangement of the members is similar to either of the two cases discussed in reference to figures 336 and 337. So here, FD is 0 and FDC is 0. And lastly, we have joint C. By observation of the free-body diagram, it is also equal to 0. That's FC is equal to 0. Okay, so that's all for the analysis of trusses using the method of sections and the analysis of space truss. Thank you.